Okay, again, good morning, everybody. So I heard that you had some issues with the lecture today. But anyway, I was also informed by some of your classmates that some resources will be posted in lieu of the lecture today. The plan would be this. as we agreed last time, I'm gonna cover some problems from worksheet number 2, those that we left over from last time. And then I'm going to proceed with examples from section 7.3 and 7.4, which is worksheet number 3. I already uploaded a blank copy of worksheet number 3 on my website, so you can take a look at it, download it, and try to answer some of the problems on your own. I highly recommend you doing that so that in the lab when we go next time, you can suggest some topics that you want to be prioritized, because I'm not sure if we will have enough time to cover everything. For worksheet number 3, I'll include all the answers at the end of the week or at the end of that worksheet. So if, say, we only answered 7 out of 10 problems, I'll include in the annotated worksheets the solution, or at least part of the solutions to the remaining 3 problems that we were not able to cover. But it will be great if you can let me know which of those questions you want to be prioritized in our lectures. So pick the hardest ones that you think, so we can work on them as a team. All right, so let's see. Let me go back to worksheet number 3. I guess there's a couple of problems that we left last time. Worksheet 2. Okay, so let me just browse it quickly. So this is still about the mean value theorem and the average values of integrals. I guess the first problem we skipped was problem number 3, but I guess this would be easy, or this would be quick. The only thing here is that that might confuse you probably is the other letters in the function f, because the function f here is defined to be mx plus b, right? And here m and b should be treated as constants. They are constant parameters. And also here the interval given is also kind of abstract. It didn't give us an exact interval. All we know that it is of the form 0 to a, and a can be any positive real number. So this is some kind of a general question, an abstract mathematical question, which will hold for any real number m, b, and a. So instead of solving a specific linear function, we are dealing with a more generic one, which will hold for any value of m, b, and a. So if you recall, for part A of this worksheet, the instruction is first to find average value, and then find a value of c that is guaranteed by the mean value theorem. So let me begin with computing the average value. And if you guys remember the formula for the average value of your function, it's 1 over the length of the interval. Here, the interval is from 0 to a, so the length would be a minus 0. It's the right endpoint minus the left endpoint. And then you integrate over the interval the given function. So the given function is mx plus b dx. But again, this differential tells us that the integration will be carried out with respect to the variable x. So all other letters or all other variables that you see in the integrand should be treated as a constant. Only x acts as a variable. So m and b inside the integral are just constants, all right? So if I carry out the integration, this will just be 1 over a. Integral of mx plus b, treating m and b as constants, would be mx squared all over 2 plus bx. And then fundamental theorem of calculus tells me I need to evaluate it starting from 0 until a. All right, all good? And then we plug in the upper bound and the lower bound, then subtract them with each other. By the way, this is worksheet number 2. We'll just complete some of the problems off of here before going to worksheet number 3. All right. So plugging in, I have 1 over a times, I plug in the upper bound. So I'll have, oh, this would be easy. So this would be m a squared all over 2. Remember, I'm plugging in x equals a plus ab. Minus, I was supposed to plug in x equals 0, but that will just give me 0 for the 2 terms, right? And then simplifying more, I'll have 1 over a times ma squared all over 2 plus ab. And then the a's will cancel somehow. So I'll have ma over 2 plus ab. Sorry, plus b, right? So that's the average value. The average value is ma over 2 plus b. That's the final answer. Because remember, a, m, and b are all constant. So here we get the constant value for the average value, all right? And then there's a follow-up question. What is the value of c where this average value is attained, right? Remember, the mean value theorem guarantees that there will exist a c between 0 and a such that the function value is equal to the average value. So that means we want to solve for c such that the function value at c is equal to the average value, ma over 2 plus b. Do you have any guess where what will this c be? Without looking at the math, just imagining it. Mx plus b is what? The graph of mx plus b is a straight line, right? From 0 to a. So can you guess somehow where will the average value occur? If it's a straight line, where do we expect the average value to be?
In the middle.
Uh-huh. Good choice. It should be the middle. And let's see if that indeed is the case. So f of c equals ma plus b. So let's work with the left-hand side first. Plug in c into the function. Remember, the function is mx plus b. We replace x by c. So we'll have mc plus b equals the average value. And then here we see that this b will be canceled, right? So I subtract b from both sides. So that will give us what? mc equals ma over 2. And then I can divide both sides by m, so I get c equals a over 2. And indeed, a over 2 is the middle of the interval, which makes sense because you have a straight line. The average value is expected to be in the middle of the interval, right? And the middle is a over 2. All right, is that good?
Yes.
All right. I'll take your silence as a yes. Don't hesitate to ask your questions. Okay. Let's see another one. Problem number 6, sort of a word problem. But here all we need to do is to apply the property or the idea of average values. So the problem is just disguised a little bit. So here we need to find the average area of all circles with radii from 6 inches to from 3 to 6 inches. So the problem here is this is a continuous problem because we want to cover or to compute the average area for circles with radii between 3 and 6 inches. It's not a discrete set of radius values, but it will go continuously from 3 to 6. So here, what do you think would be the function f? So we know that we need to find the average value, right? But what would be the function f? Any idea? What would be the function f which we want to get the average value of? Daryl, you're correct. So the function value or the function that we want to get the average value of is the function that gives us the area of a circle, right? And the formula for a circle is pi r squared, where r is the radius. So the function we need to take the average value of here is the formula for the area of the circle, pi r squared. And what is the interval? So the interval here is r ranging from 3 until 6. Okay, so the average value will then be 1 over the length of the interval. So our interval is from 3 to 6. So the length would be 6 minus 3. Then integral from 3 to 6 of the function f dr, all right? So here the variable of integration is r. And then we evaluate. So I'm going to have 1/3. And then the integral would be pi r cubed all over 3, evaluated from 3 to 6. And then this would be 1/3, or probably I'll write it as 1/9. and then pi times 6 cubed minus 3 cubed, right? And that could be your answer. I'll leave it this way because I don't want to commit that silly algebra mistake again. A reminder, last time I guess I had a mistake. I took 15 times 6 as 80 instead of 90. So that's a reminder that you guys need to double check my arithmetic. I hate doing arithmetic. So let's see. Maybe I can use a calculator here. So it seems that here I'll do 6 cubed minus 3 cubed. That's going to be 189. So this would be 189 pi over 9. Okay. Well, actually, I can further simplify this as 21 pi. Right? Okay, good so far? And I guess there's only one question left from this worksheet. Okay, number 7. This is kind of a proving problem. So here we have a continuous function f, and we want to prove that if f is an odd function, then its average value over any interval of the form negative a to a is 0. First, we need to recall what an odd function is, right? So here, a function f is odd if and only if. Oh, by the way, I use IFF for the phrase if and only if. It's true if and only if f of negative x equals negative f of x. Example of odd functions are what? X cubed, x to the 5th, x to the 7th. And you see that if you plug in negative value, that will be the negative of the value of the positive x, right? So f of negative x equals negative f of x, right? And we want to show, what do we want to prove? We want to prove that the average value over any interval of the form is 0. So the only way to prove it is to compute the average value and check if it is indeed equal to 0. So let's compute the average value of such a function. It's 1 over the length of the interval. The interval is from negative a to a, so the length would be a minus negative a. That's right minus left bound. Integral from negative a to a of f of x dx, right? Formula for average value. And then we can manipulate this as 1 over 2a. And then what I'm going to do is to split the integral up into two pieces. Negative a to 0 of f of x dx plus integral from 0 to a of f of x dx. Okay. Any idea why I decided to do this? Why did I want to split the integral into two pieces? Because it seems unnatural to do that, except if you know something about the function f, right? So why did you think I resorted to this?
Because
all
it's
right.
symmetrical, it would equal 0 or something. I don't know.
Yeah, something along those lines. Yeah, Maria, Daryl, yeah, you're correct. I'm hoping to use the property of the function being odd. And I'm hoping that, as what John mentioned, I'm hoping that some things will cancel out because I'm expecting the answer to be equal to 0. So, but look at this information about odd functions. The function value of negative x's is equal to the negative of f of x. So that's why I decided maybe I can split this two up into two pieces, right? And then maybe I can do it this way. So note that, how do I want to do this? So maybe I'll use the same trick as what I used last time. So I look at one of the intervals. So probably I look at, okay, oops. So I look at the first integral, for instance, negative a to 0 of f of x dx. And for me to be able to use this info, about odd functions, I need to have a negative inside the function. So what I'll do here is I will let u to be equal to negative x. Okay, and then if that is the case, then du would be what? Du would be negative dx, right? And so this definite integral, the integral from negative a to 0, can be rewritten as f of x. F of x will be f of negative u, right? Because from here, I can solve for x and I'll see that x is equal to negative u. So the x in the original integrand was replaced by negative u, and then dx will be replaced by negative du, and then the bounds would be from a to 0. Okay, is that substitution good? Okay, and then if that is well, then I can proceed with the next step. So I took the negative, I took the negative sign out of the du, right? Put it outside. But look at this. I have the bounds are from a to 0, but I'm expecting it to cancel with the second integral that we had above, right? So I will interchange the order. Instead of a to 0, I'm going to do integral from 0 to a, and that comes at the cost of putting another negative sign, right? Yeah, John, that's correct. I needed to change also the bounds. Remember, whenever using u substitution, once you change the variables to u, the bounds should also change. These bounds are for x. X equals negative a and x equals 0. Now, the next set of bounds would be bounds for u because the variable now in the second integral or in the second equality here is in terms of u. Yeah, thank you for pointing that out. So now, okay, there we go. So we have this. Do you guys agree with this last step, the third equality? And then I'll do a superficial change of variable. I'm going to change back to x, right? And again, you can think of it as just a superficial change in variables, but the thing here is I change, I let what u equals x here just to make a superficial change in the variables, so you see that everything works well. And yeah, so what do we have here? I'll use the fact that the function f is odd. Remember what we said earlier? It's an odd function if f of negative x is equal to negative f of x. But here I have f of negative x. Using the fact that f is odd, then this is negative f of x dx. And that guy becomes negative integral from 0 to a of f of x dx, right? Which perfectly fits to our agenda of having it cancel with the second term. Because remember, we have this. I'll just copy this over. So now we know that the average value from our earlier analysis was this. Okay. And we just learned that the first integral is the negative of the integral from 0 to a of f of x dx plus the second term f of x dx. And look at these two guys. They will cancel each other out, right? Because they are exactly the same except for their signs. So now we have proven indeed that the average value of any odd function over an interval of the form negative a to a is equal to 0. Good, guys? That was quite long, but I hope you understand the process. Okay, so basically, this is how you answer word problems. You start reading the problem, make sure you understand what it is really asking for, and then the second step is to digest all the information the problem gives you. You have phrases, interpret them mathematically. It would be good if you can write them on paper and then write them in terms of mathematical sentences, and then do the thing. Do all the calculations towards the end goal of answering the problem. Okay. So I guess that completes worksheet number 2. I guess I got a question here from John from the chat. Any particular problem with this, John? Because I'm thinking this is pretty straightforward. Any difficulty you had with this one?
I had a hard time getting the C value. I mean, I could get the average value really easily, but I've never worked with something where you can do 1 minus, this square root stuff.
Mm-hmm. Okay, let me see. So, right. So, are you sure that the average value is 8/3?
I thought it was. I don't know. I might be wrong. I did it like last night, maybe even 2
Uh-huh.
days ago. So,
Okay, yeah, let me try. I was just asking because so that will save me time from calculating it. But anyway, so
yeah.
to answer your question, I'll just say it's additional question. You're looking for the average value, right? So for those for you guys that John sent a question in the chat. So if you're wondering where this comes from, so the average value is 1 over the length of the interval. The interval is from 0 to 2, so it's going to be 0 to 2. The length would be 2 rather. Then the function f is 8x minus 4x squared dx. So I compute for the integral, it's going to be 1/2. Then I'll have what? I'll have 8x squared all over 2 minus 4x cubed all over 3, evaluated from 0 to 2. And then I will factor out the 4 before doing the substitution because I don't want to work with large numbers. So I'll have 2 here, and then I'll have 2x squared over 2. So this would be x squared, and then minus 2/3 x cubed. I hope that's correct. Evaluated from 0 to 2, and then plugging in 2, I'll have 4 minus 2/3 times 8. So this would be 2 times 4 minus 16/3. I guess I did something wrong. So why do I have this? Perhaps factor out 4. Oh yeah. I factored out 4, so that should be 1/3. Okay. Then this is 1/3. Then this is 1/3. This would be 8/3. Okay. And then we'll have 2 times 12, 4/3. And that's going to be 8/3. So yeah, the average value is indeed 8/3. And then we're looking for the value of c such that f of c equals the average value. So you plug in c into your function f. So you'll have 8c minus 4c squared equals the average value 8/3. And maybe it would be helpful if you multiply all sides by 3 so that you get rid of the fraction. So I'll have 24c minus 12c squared equals 8. And then I'll have 12c squared. I'll just put everything in one side of the equation. Minus 24c plus 8 equals 0. So I transferred everything to the right and flipped the equation. And then these are large numbers, but I can divide all of them by 4 so that I'll be left with what? 3c squared minus 6c plus 2 equals 0. And I guess this is something that is not factorable, so you need to use the quadratic formula. I guess that's what you missed using the quadratic formula. Quadratic formula is c equals um, maybe negative. Well, I want to write the general form, but it will mess with the letter c here. But if you recall, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is the coefficient of x squared, b is the coefficient of x, and c is the constant value. So in this case, the variable is c. It should be equal to 6 plus or minus the square root of coefficient of c is 6. Oops. It's going to be 36 minus 4 times a. So that's going to be 12. times 2, that's going to be 24 all over 2 times 3. So this would be 6 plus or minus root 8 all over 6, which will be 6 plus or minus 2 root 2 all over 6. And this would be, oh wait, this is not 8, that should be 12. And you see that indeed you need to check my arithmetic. So this would be 2 root 3. And then simplify, you'll get 1 plus or minus root 3 all over 3, right? Oh, I guess you get the right idea here, though you have two options. So you either have, you need to verify if both of them qualify as the value for C. Well, remember that the mean value theorem only guarantees this a C between or over the interval given. So I guess the interval given to you is from 0 to 2, right? So you need to check, are these numbers between 0 and 2? Now, what do we know about root 3 over 3? Root 3 over 3 is what? This is something that is less than 1. Yeah, this is less than 1. So that means if you add it to 1, you'll get something less than 2. If you subtract it from 1, you get something greater than 0. So I guess both of them qualify as the values for C. So here, your answer should be both 1 plus and minus root 3 over 3. Okay, does that make sense, John?
Yeah, that was really helpful. Thank you.
Okay, and to the others, how about it? Is it good? All right, I'll take again your silence as a yes. I hope that helped. Okay. Let me see. Herson sent a question. Okay, now in that particular question, you can do a long version of the solution. In that question, you have f of x equals absolute value of 4x over the interval -6 to 6, right? And the long solution to find the average value is to do the integral, right? So remember, the average value is the integral is 1 over the length of the interval, integral from -6 to 6 of absolute value 4x dx. Yeah, the thing is you can split the integral first from -6 to 0 and then 0 to 6, and then carry out those integration independent of each other. I guess we solved a problem like this either last Friday or last Monday, so you can share our video recordings with your friend Herson or the annotated worksheet. I give everybody access to my site, and the videos, I also post them. I guess now they are posted in YouTube, so you're free to share them with your friends with whom you think it would be helpful. But another solution, because there's an alternative one which would be much easier, is to identify, which I want to share with you guys because I haven't given it as an example last time. What do you notice about the absolute value of 4x? Again, its graph is symmetric with respect to x equals 0, right? So its graph is something like this, just a more expanded V-shaped graph, which is symmetric with respect to 0. And whenever you have, Muriel, you can separate them again from -6 to 0 and then 0 to 6, then do the integration thing, but that will take long. This is similar to what we answered last time, the absolute value of x, I guess, on top of this worksheet. But another alternative way is to use the fact that f is even, right? So, and I guess we had an example last time where we have proven that, yeah, Daryl is correct. I can, instead of splitting this up into 2, I can do it as 1 over 12 times 2 integral from 0 to 6 of 4x dx. Just one half. I'll just evaluate one integral, but I know that they are symmetric with respect to the x-axis, so I can just compute this and then multiply the result by 2. And that's perfectly fine. So you don't have to compute the other integral from -6 to 0. It's fine if you didn't think of this, but this will save you a lot of time solving this, especially if this was in an exam. So the property of odd and even functions. If it was an odd function, automatically it's equal to 0. If it's an even function, and then it would be twice of the integral of 1/2 of the entire interval. So, okay. So if that is good, then let's jump to worksheet number 3. So I hope I didn't go too fast. This is not my usual pace. I usually am a lot more slower explaining things like that because I really want to explain things in more details. But I hope you guys get the idea. Just let me know if I went too fast. Okay, worksheet number 3. Worksheet number 3 covers an application of integrals, in particular in computing areas and volumes using integrals. You started with section 7.3, I believe, in the lecture last Monday. So let's answer some of the problems there. But I'll do a quick recap of the ideas so that you get refreshed, and probably some of the questions here are not very basic as what you would expect as an introductory example, because I again assume that these were already tackled in class, and the lab serves as a supplementary venue for the lecture. But anyway, a quick recap of the concept that you need here for computing areas. Right. So integrals are very useful in computing areas of arbitrarily shaped regions. Actually, this is basically how we derived, or how we prove, the formulas for areas that you know. How come we know that the area of a triangle is 1/2 base times height? How do we know that the formula for the area of a circle is pi r squared? And all of those things. Or have you ever wondered, how are land surveyors able to compute the area of lots that are irregularly shaped? I don't know here in the US, but back in my country, in the Philippines, the shape of lots or patches of lands vary. They are not rectangular, they are not trapezoidal in nature. They can be arbitrary because they are usually bounded by rivers and so on. But how come surveyors can still compute the area of those irregularly shaped lots, where we just know formulas for squares, circles, oblongs, trapezoids, whatever quadrilateral or polygons we have, right? The idea comes in using analysis or integrals. So how do we compute areas then? So if I have an arbitrary region, say bounded by a function y equals f of x above, and bounded below by another function y equals g of x, right? And I want to compute the area over the interval a to b. Okay, so from a to b, so I want to get the area of the shaded region. Okay, that's my shaded region, right? And the problem is, what is the area? Okay, now the idea here is that the area can be calculated easily using integrals. So the general idea is this would be, we use some sort of a strips. So here I'll draw a vertical strip. And this is the first point. Whenever using vertical strips, the variable of integration should be x. So vertical strips, if you are computing the area using vertical strips, which I will later just call VS, you use x as variable of integration. This also holds for section 6.4, so I hope you guys will remember this. Vertical strips always use dx, or x is the variable of integration. And since you have dx, the bounds for your integral should be bounds for x. what are the x values that is covered by the region? Well, the region started at x equals a, and it lasted until x equals b. So the bounds for the integral will be from little a to b. All right. And then what would be the integrand? The integrand supposedly is the height of the vertical strip. And how do we compute the height of the vertical strip? The height of the vertical strip would be just the upper function minus the lower function. So basically here, the integral would be f of x minus g of x. And you evaluate this integral, whatever the answer is, that would be the area of the shaded region. And you see how easy it is, because it doesn't matter how wiggly or how irregularly shaped the region is, as long as you can identify what is the top function, what is the lower function, and then just set up the integral as top minus bottom, evaluated from the starting x value until the ending x value, and that's it. That would be the area of the region. Okay? Now, there's another version, but with horizontal strips involved. An example would be this. If I have, say, a function like this, right? So say this is x equals g of y, and then I have another function, maybe somewhere here, a wiggly function. Okay. Say this is x equals, why did I use g there? Anyway, h of y. Okay, let me change the function here because that will be complicated. Let me just do the right function there. Yeah. Okay. Or let me call it f. Okay, so now if you are to use horizontal strips to compute the area of the shaded region, okay, so you always use the variable y. So for horizontal strips, I'll call it hs later. You use y as variable of integration. Okay. And then since y is the variable of integration, the bounds for the integral should be bounds for y. So you need to identify what is the starting y value. Say this is c, the starting y value. And maybe this is the ending y value for the region. Let's call that d. So the integral or the integration should be performed from c until d. And then the integrand would be the width of the horizontal strip, right? I forgot to shade the region, so this is the shaded region. Now, how do we compute the width of the horizontal strip? It would be the right function minus the left function. So here, the right function is f of y minus the left function, that's g of y. Okay? So again, dx, it's top minus bottom. If it's dy, it's going to be right minus left, which brings us to one important point. If you want to accurately set up the integral that will give you the area of a shaded region, you should have at least have a good idea of how the graph looks like. Because you need to identify what is the graph on top and what is the graph or what is the function at the bottom. Or in case of horizontal strips, what's the graph on the right and what's the graph on the left. Okay? Any questions with that? I hope that general description of the procedure makes sense. And then let's try answering some problems. I hope you have seen some basic examples in the lecture. Is that correct? So I won't have to go to very basic ones.
Yeah, we've seen absolute basic questions.
Okay, so let's do the more challenging ones. So let's start with problem number 1 in this worksheet. So in problem number 1, maybe I should copy paste it. Okay. Right, so here we need to find the area of the triangle with vertices at 0, 0, 1, 5, and 1, 6. Of course, you can use your your geometry, your knowledge about geometry, how to compute the area, but I'll use calculus to do this. Okay, first I need to have a sort of a general picture of how the triangle looks like so I can identify what are the functions involved. First vertex occurs at 0, 0. Second vertex at 1, 5. Say 1 is here. Let's say 5 is here. In all of my graphs are drawn not to scale, so I'll just put some proper labels to them. And then the third vertex is at 1, 6. So let's say 6 is over here. Okay. And then here I'll have, this is my triangle. Okay. And we want to find the area of this triangle. But since we're using calculus techniques here, yeah, this is an odd looking triangle. So probably it will take a lot of concepts from geometry to be able to rotate this triangle to get the area of this using geometry techniques, right? But let's use calculus, and the requirement for the calculus technique here is to identify what is the top and what is the bottom function, because my goal here is to use vertical strips like this one, right? So in order to use vertical strips, I must be able to compute the length of that vertical strip using top minus bottom, right? So I need to figure out what's the equation of the red line and what's the equation of the blue line. So if you still remember, you can compute that using the point slope form of a line. So this line, this function, I'll call it f. This is between 0, 0 and 1, 6. If you remember how to compute how to find the equation of a line, so it's y minus one of the y values. I'll choose that would be my y value, equals, or maybe I'll write the formula for you to remember it. Y1 equals m, which is the slope, x minus x1. So I'm going to pick y1 to be this. I'll use this as my x1, right? You can also use 1 and 6, so it's up to you, but it's easier to work with those with those two zeros. So this would be y minus 0 equals the slope. The slope is change in y over change in x times x minus 0. So we find out that the equation of the red line is y equals f of x equals 6x. And then if you do the similar analysis, so similarly, I'll call G the graph between, or the line between 0, 0 and 1, 5. If you do the same analysis, you get y equals g of x equals 5x, right? And then now it's easy because to find the area, I'll simply do the same trick. I'm using vertical strips. Vertical strips, I need a dx. And then since I have dx, I need to find the bounds for x. This is the shaded region. It started at this x value here, which we know is 0. And ended up with the x value here, which is 1. So the bounds would be from 0 to 1. Top function is 6x. Lower function is 5x. And that's going to be the integrand. And so all we need to do is to evaluate this integral. So we have x dx, and that would be x squared over 2, evaluated from 0 to 1. And that's going to be 1/2. So the area of that triangle is 1/2. Good? Hello, guys. You still there? I hope that made sense.
A lot of sense.
Okay.
Wait, so you do the same thing with g of x as you did with f of x, right?
Yeah, to get the equation 5x.
Okay, and then you just subtract them and you do the, okay, thank you.
Right. So, okay, all good. Let's write problem 2. Problem 2 is a bit more involved. At least not not as far as calculus is concerned, but the graphing would be a little bit more involved, because remember, the first step is to have a nice idea of how the graph looks like. I'm not sure. I was thinking, should this be a later example? But because y equals x is easy, it's just a straight line. But 5x minus x cubed, that's a cubic function, and the graph will look a little difficult to picture, right? Because we are just used to sketching y equals x cubed, not 5x minus x cubed. So let's see. The thing here is I need to make sure which graph is on top and which graph is on the bottom, right? So I need to sketch the graph. Right? But in particular, I want to focus on y equals 5x minus x cubed. Let me call this f of x, right? How do we sketch graphs of higher order polynomials? I guess this should shook your memories, because here we need to do curve sketching all over again.
So we go right 5 and then just a negative cubic function.
But we need to subtract them, so the function values might not be easy to find, because the minuend is scaled by a factor of 5, so it won't be that straightforward. So unfortunately, I'm running out of time, but probably I can start the solution, and then we'll go over it on we'll finish it up on Friday. But the thing here is I will use curve sketching techniques. Do you still guys remember this? From Cal 1? So that we'll have an idea whether the graph is increasing or decreasing, where it is concave up or concave down, so that I know exactly, or I'll have a good idea how the graph looks like. So yeah, this is something from Cal 1. So first I need to use to find f prime, the derivative. This is 5x minus, it's going to be 5 minus 3x squared. And then I'll put this equal to 0. So that means if you carry out the algebra carefully, you get x equals plus or minus root of 5/3. Is it okay if I skip some of the algebra parts?
Yes.
So yeah, you can retrace it. And then remember, you do a sign chart for f prime. So you know when is the function increasing or decreasing, using these critical numbers as your subdivision points. So the first test point is negative root of 5/3. The second test number is root of 5/3, or not the test points. These are your subdivision points, right? And then we want to find what is the sign of f prime over these intervals. So to find that, we need some test numbers. So here I'll use test number -2. Here I'll use test number 0, and I'll use here test number 2. So it doesn't matter what constant you use on those subintervals, just make sure that they are indeed on those intervals. So here I know that 5/3 is less than 1. So it's less than 4, because that's 1.16, I guess, or 1.66, somewhere around that. So in square root of 1.66 is less than square root of 4. So I know that -2 is to the left of negative root of 5/3. And if I plug in -2 into the derivative, I'll get a negative sign. And then I'll plug in 0, I get a positive sign. And if I plug in +2 into f prime, I get negative. So I know over this interval, the function is decreasing. Over this interval, the function is increasing. And over this interval, the function is decreasing. So, and then what can we say more? We know that there is, So there is a local, a local minimum at x equals negative root of 5/3, and a local maximum at x equals root of 5/3, right? And the function values are what? F of x is, if we plug in negative 5/3, I computed it before, and it is negative 5 root of 5/3. And here the local maximum value is 5 root of 5/3. Okay. And then, oh, it's already time. So maybe I'll stop here. I just want to remind you why am I doing this? I'm doing this so that I'll have a good idea of how the graph looks like. Because having a good idea of how the graph looks like is a prerequisite, because I need to identify what is the function on top and what is the function in the bottom, right? So what I'm doing here is I'm using techniques from Cal 1, curve sketching techniques. Here, I'm looking for f prime, looking at the sign of f prime, which will tell me when is the function increasing or decreasing. And it also revealed local minimum and a local maximum for the function, which gives me a good idea of how the function behaves. Now, I need to do a second step, which is look at the concavity of the graph. And in that case, I need to compute for f double prime and look at its sign, right? So I guess it's a good time to stop here. So what I will ask you guys to do is to try to remember how you do curve sketching from Cal 1 so that you can complete this this part of the solution. So what I will do is when I upload the annotated worksheets for today, the completed worksheet 2 and the start of worksheet 3, I'm going to include the actual graph of this function already, but I hope you guys reread your notes from Cal 1 to remember how I did it, so that at the start of our meeting on Friday, I can start on setting up the integral that will give us the area of the region. Is that fair? What do you think, guys?
Sounds good. Yep.
So yeah, if you had some difficulties with remembering curve sketching techniques, or you have some questions, just let me know at the start of the lecture. But I will of the lab next Friday. I just want to sort of save some time because I think you can do this, guys. You passed Cal 1, so this should be easy for you. So with that being said, let's call it a day here. So I hope you enjoy the rest of your day, and see you once more on Friday. Bye, everyone.